Hello class, hello industry physics. Welcome to our last lesson, which is actually going to cover the fifth exam, really the final exam for class. And this is going to be on geometric optics, also called ray optics, where we're going to view light not as an oscillating wave, but as specifically rays that travel in straight lines. And these rays can reflect off of surfaces, or they can refract into a new material. And in your exam, you're going to have two key formulas, where n is the refractive index, n1 is the first layer a ray is traveling through, or the current layer, and n2 is the refractive index of the layer that we are approaching. Theta I is going to be the incident angle, or the angle approaching our boundary between n1 and n2. Theta R is our angle of refraction, or the angle once that ray refracts into the next layer. And this is our sine function. Rearranging these to solve for theta R, that'll be arc sine or sine inverse, either button on your calculator, of n1 sine of theta I over n2. And if we have a situation where n2 is greater than n1, n1 sine of theta c, our critical angle, equals n2 sine of 90 degrees. Sine of 90 degrees just equals 1. So, solving for theta c, the critical angle is arc sine or sine inverse of n2 over n1. We only need to worry about critical angles if we have a ray that's approaching a layer that has a lower refractive index than the one we're currently in. Refractive indices, that's sort of like density in a way. Let's say we have a ray that's traveling at a certain angle, and the angle that we care about is between the axis that is perpendicular to our boundary between one material and the next. The angle between this perpendicular axis and our ray, those are the angles that we're solving for. Let's say we have a material flowing through a ray that's flowing through some material where the refractive index is 1, and then it approaches a material where the refractive index is 2. Well, there's two possibilities. The ray may sometimes reflect or may sometimes refract. If we are increasing in refractive index in n values, we're just going to assume that we're refracting because it's a possibility. Now, as that ray refracts into a new layer, it likes to bend toward the material that had a higher refractive index. So this angle of incidence here is going to be higher than our angle of refraction here. So the ray is bending toward the second layer because it has a high refractive index. Now, whatever angle we get for theta R, that angle is going to become our new theta I, the incident angle for the next layer. And if we determine that it's possible, and since the third layer has a higher refractive index than the previous layer, we're just going to assume that the ray will refract. We'll use the previous theta R as our new theta I to then solve for our last theta R. And as we see, as we're drawing this ray, if we're increasing in refractive index, you should be drawing that ray getting steeper and steeper. Now, in the case of the opposite, where we're starting in a layer that has a high refractive index and approaching a layer with a lower refractive index, we'll need to calculate a critical angle to see if our incident angle is less than the critical angle. But before we cover that, if we have decreasing refractive indices and values, and we determine that the ray is able to refract into the next layer, it should be bending toward the original higher refractive index layer. So this ray is going to bend toward this boundary by having a greater angle of refraction than the angle of incidence in the prior layer. And that theta r becomes the new theta I. And if the next layer also has a lower refractive index, then we should calculate theta r as an even greater value, basically getting even broader. Our values are going to be theta I for incident angles, theta r for refracted angles, theta c for critical angles, and if we have the situation, theta REFL for reflection for the reflected angle. Essentially, if we have a situation where our current refractive index is higher than the one we're approaching, there's a possibility that that ray might not be able to refract, and if so, it's going to reflect. What we're going to see is we're going to calculate theta c based off of the formula from the prior page, and if theta I is less than theta c, then it's possible to refract into the next layer. If theta I equals theta c, then the ray will refract at a 90-degree angle. So basically between both layers. And if theta I is greater than theta c, then it's impossible to refract. And at that point, we're just going to draw the ray as reflecting off of our boundary instead of refracting. And then we'll stop there. If we ever have a point of reflection, guaranteed reflection, 0% refraction, or if we've managed to refract through all layers, that's your stopping point. Now, getting to our problem. On the left side, we have a multilayer that involves a ray of light traveling first through air, and that layer is on top of water, which is on top of cubic zirconium, which is on top of a layer of diamond. And the refractive indices are 1, 1.33, 2.16, and 2.42 for air, water, cubic zirconium, and diamond respectively. Well, as we look at this refractive index, let's see. Here we go. As we look at this multi-layer on the left side, our incident angle in the first layer is 45 degrees. Our N1, the current layer, is going to be N equals 1 for air, and N2, the next layer, is going to be N equals 1.33. Well, theta R1, that will be the first refractive angle we calculate after refracting past layer 1. We can just skip to this step because air has a lower refractive index than water. We're currently in air. We're going to refract into water. Since the refractive index is increasing, we're just going to assume that we're refracting because that's always a possibility when N1 is less than N2. So we're going to calculate this angle, theta R1. Theta R1 equals arc sine or sine inverse of N1, which equals 1, times sine of our incident angle in the first layer, 45 degrees, divided by N2, which was 1.33. And if you have your calculators set to degrees, not radians, have your calculator in degrees, then your answer should come out to be 32.12 degrees. We're going to label that on our graph as theta R1. And it might be a little difficult to make this a little steeper than the 45 degrees, so it's okay if it's roughly estimated. But theta R1, this is 32.12 degrees. This ray of light is now approaching a cubic zirconium layer while traveling through water. So now the incident angle here, theta I2, is just the same value as theta R1 based off of trigonometry. So water has a lower refractive index than cubic zirconium. It's possible to refract into the next layer without us doing any additional check. So let's solve for theta R2, the refracted angle after leaving the second layer. Well, again, theta I2, our new incident angle in our second layer, equals the refracted angle from the first layer. So 32.12 degrees equals theta I2. Theta R2 will be sine inverse of the current refractive index, which for water is 1.33, times sine of the incident angle, so sine of 32.12 degrees, and then the refracted index of the next layer, which for cubic zirconium is 2.16. And all of this should end up equaling 19.11 degrees in your calculator. So labeling that as theta R2 here, the perpendicular axis to our boundaries between two layers, the angle between the perpendicular axis and our refracted ray will be theta R2. Now, 32 degrees versus 19 degrees. 19 degrees, that's steeper, so that's why I'm drawing this more closer to being vertical than the prior ray. Now, we are approaching another layer, diamond, which has a higher refractive index, which means we're going to assume that we are refracting. Therefore, theta R2 is going to equal our new theta I, or theta I3, and that is a typo there. That should say theta I3. There we go. So our prior calculated theta R2, that is our new incident angle theta I3, the incident angle as our ray approaches this diamond layer. Since the refractive index is increasing from the current layer to the next layer, we're going to assume that we're refracting, and we're going to calculate theta R3 based off of theta I3. And theta R2 is just what we use to equal theta I3, or 19.11 degrees. So theta R3 will be arc sine of the current refractive index, 2.16, times sine of 19.11 degrees divided by the oncoming refractive index, the next layer being 2.42. And all this will end up equaling 16.99 degrees. So once again, our ray is going to be even steeper now, going from 19 to roughly 17 degrees. And that's how you should do this plot, basically trying to make this ray look like it's getting steeper and steeper. We just made it into the last layer, which means we can stop for this multi-layer. Labeling each one as theta R1, theta I2, theta R2, theta I3, and theta R3. And if we label them so, then if we say what they equal elsewhere, then that's good enough for this side. Now on the reverse side, this multi-layer, we have a ray of light starting from the diamond layer, going up to cubic zirconium, then water, then air, potentially. Since the refractive index in our current layer is lower than the oncoming layer, there's a chance that refraction might actually be impossible. That's why we're going to calculate theta C1, or the first critical angle. That's going to be sine inverse of the oncoming refractive index divided by the current refractive index. So 2.16 divided by 2.42. And that equals 63.2 degrees. Never use the critical angle in any further calculation. This is just to be a check that we compare our current incident angle, which is currently 30 degrees. Our incident angle, theta I1, is less than our critical angle, theta C1. That means, since 30 is less than 63, it's possible for this ray to refract into the next layer. So now, we're just going to calculate theta R like normal. Theta R1 is sine inverse of N1, the current refractive index, 2.42, times sine of our incident angle, not our critical angle, but the incident angle of 30 degrees, divided by N2, or the oncoming refractive index, 2.16. Therefore, theta R1 now equals 34.07 degrees. So, our ray refracts into the next layer. Theta R1 would be this angle here, which is going to equal theta I2, the angle as our ray is approaching this next boundary of water. Water has a lower refractive index than cubic zirconium, so we're going to need to calculate theta C2, or the critical angle between water and cubic zirconium. Well, that's theta C2 will be sine inverse or arc sine of N2 over N1. So 1.33 over 2.16, that equals 38.01. We know that theta R1 equals theta I2. That's based off of trigonometry. So the angle we care about now is theta I2. This is equal to 34 degrees, 34.07 degrees, which is less than our critical angle, 38.01 degrees. Therefore, it's possible to calculate theta R2 as sine inverse of the current refractive index, 2.16, as we're traveling through cubic zirconium approaching water, times the angle of incidence, sine of 34.07 degrees, divided by the refractive index of the next layer, which would be water of 1.33. And if you have this all set up in your calculator correctly, you should get 65.48 degrees. Now that's theta R2, and that is going to be used as the value for theta I3, the incident angle as this ray traveling through water approaches the boundary between water and air, which is once again seeing a decrease in refractive index, so we need to calculate our critical angle theta C3. Theta C3 equals sine inverse of the refractive index of air, the next layer, over the current layer, water, 1.33. So sine inverse of 1 over 1.33 equals 48.75 degrees. We know that theta R2, our refracted angle off of the second layer equals the incident angle in the third layer. And that equals 65 degrees. And that is greater than theta C3, or our critical angle of 48 degrees. Because the incident angle is greater than the critical angle, it is impossible to refract into the next layer. There is 0% chance of refraction, which means instead of having the option to reflect or refract, it is only ever going to reflect. Therefore, theta I3 is going to be used as the value for theta REFL, theta reflection. Therefore, instead of drawing the ray as refracting into the next layer, just draw it as reflecting. And since this is the first time we have a reflection, a guaranteed reflection from 0% chance of refraction, we stop this multi-layer problem here. And that should be how you draw and sketch and calculate for your final test. It has been a pleasure to have you all in class for this class on industry physics, covering so many different topics. Yeah, it's been a pleasure to have you all. For those of you in class, I hope you enjoyed this semester. I definitely have enjoyed having you all in class. You've been very chill, and I've appreciated you all registering for a class that helps me teach at a time that I like to teach, and honestly, gives me some extra spending money. For those of you who are just watching the video, if you would like to, you're more than welcome to like the video, subscribe to the channel, do really anything you want. Leave a comment if it's actually relevant to your college course or beyond or before. No matter what though, pleasure to have you all. Wish you all the best on your studies, and peace.